Okay, so the most important thing is exam 2 is on Friday. And that is going to cover everything. So the topics are everything up through structures. So no internal loads. Anybody have any questions about the test? Any homework questions you want me to go over? All right. So last time I brought up this problem. We had a beam. It's a cantilever connected to the wall at the right side. And, whoops, not that. This. It was 3 meters long. There was a distributed load of 1,000 newtons per meter on this side. And the mass was 50 kilograms. And a free body diagram of the whole thing. Well, we had this, a couple at the wall. We have this distributed load. And we also have another distributed load from the weight force. That's a uniform one. And that has a magnitude of the total weight, which is 490.5 divided by 3. So that's 163.5 newtons per meter. And so this is 2 distributed load functions. The first one, the triangular, as a function of x, is 333x. That's just the y equals mx plus b equation for that line of the top of that triangle. And then the second one is just a constant function, 163.5. And so the total function q is the sum of these two. So that's 333x plus 163.5. Okay, so when we go through this problem, we're going to get a shear force function. And if we take the negative derivative with respect to x of the shear force function, we need to match this total q function. Okay. These are the endpoints. And then there's nowhere in between the two endpoints where you have point loads or a change in the distributed load function. So we're just going to need one cut for this. So this is valid for any x's between 0 and 3. We have a piece of the triangular distributed load, but we're missing a bunch of stuff over on the right. So this doesn't come all the way to a height of 1,000 Newton meters. We have this rectangular distributed load that's easier to deal with. And we have the internal loads. The height of this, that's the easy one. That's just 163.5. And the height of this one comes from that distributed load function, Q triangle. We know that the height for a given x value is this. So since the right end is our x, value x, the height of the triangle at that right end is 333.3 repeating times x. And so now we can figure out how to represent these as point loads. If you think about the triangle, it has a width of x and a height of 333x. We know that the location of the centroid is 2/3 of the whole base of the triangle, so this is 2x over 3. And the area is just the area of a triangle, 333x, the height times the base divided by 2. So that's 166.6 repeating x squared. And then we have to think about the rectangle too. That also has a width of x. The centroid is right in the middle. So if you're measuring from the left side to the centroid, that's x over 2. The height of this rectangle is 163.5. So this is the area of the triangle. The area of the rectangle is 163.5 times x, 163.5x. So now we finally have everything we need to represent this stuff as point forces. So the free body diagram for the cut we have the internal loads. Then at the center of the beam, we have a force 163.5x. And 2/3 of the way from the left to the right, we have 166.6 repeating x squared. The distance to the 163.5x is x over 2. To the 166.6 x squared is 2x over 3, and then to the end of the beam is x. Okay, so Newton's second law says 0, negative 166.6 repeating x squared plus 0, negative 163.5x plus t negative v is equal to zeros. So t is 0, and v is negative 166.6 repeating x squared minus 163.5x. And then the moment equation, the 163.5x, would this make this rotate? I'm still using the same about point as always. Would the 163.5x make it rotate clockwise or counterclockwise? Any other guesses? Yeah, clockwise.
I know the way clockwise.
Yeah, right.
He's looking at it backwards.
From the behind the wall.
Yeah.
Southern hemisphere.
Yeah, right. Okay, so we got negative x over 2, 163.5x. Another clockwise moment from the triangular distributed load. That moment arm is 2x over 3. The force is 166.6 repeating x squared. And then plus m minus vx is equal to 0. So we got m is equal to the second, I'm going to put the second term in first because it has the higher order. So 2/3 of 166.6 repeating is 111.1 repeating, x to the third. Plus, now the first term above, what's that, 81.75?
Yeah, that looks right.
Okay, x squared. And then plus vx. Now substitute in the function for v. And you get 111.1 repeating x cubed plus 81.75 x squared minus 166.6 repeating x squared times x, so that's another x cubed, minus 163.5x times another x, so that's x squared. Combine the terms, and you get m is equal to negative 55.5 repeating x cubed minus 81.75 x squared. Okay. So now let's do the derivative checks. dm dx is negative 166.6 repeating x squared. And we have that term in the shear force. This is negative 163.5 times x negative, and we have that in the shear force. Okay, that's good. And now we're going to take negative dv dx and check that against our total q function. So negative ddx of this first term is positive 333.3 repeating x. And if we go all the way up to our total q function, we have that term. And negative ddx of this second term is positive 163.5. And we have that. Yes?
So the only reason we built that q of x function was to check at the end?
Yeah. Mm-hmm.
Because when you're doing it, you have to use the point forces.
Yeah, right. So when you're doing it, each one of those separate distributed loads just treat it by itself. Okay. Any other questions about that? Okay, so finally, I'm going to get this in your notes. These are the checks you can use. First are the two derivative ones. Actually, to be honest, these are the only ones I really ever use, but I'll tell you 3 other ones you can check at the endpoints. So first, dm dx is equal to v. Second, negative dv dx is equal to q. And now at the endpoints, at any endpoint, v equals 0 if and only if there's no vertical point force at that endpoint. Okay, that's kind of wordy, but what this is saying is, say you're looking at the left endpoint.
There's no constants in your equations.
Yeah, so let's look at the left endpoint here. So there's no vertical point force at that left endpoint, right? Mm-hmm. That says that the shear force at that point has to be equal to 0. Okay? And if there was a vertical point force there, your shear force would be non-zero. Okay, maybe you can guess the other two. At the endpoint, the tension is equal to 0 if and only if, what do you think?
No vertical.
No horizontal point force, yep. And then the last one, at the endpoint, m is equal to 0 if and only if, what do you think that's going to be? No point couple. At that endpoint. Okay, so this is one where we know that at the left endpoint, okay, so let's think about the same problem again. In this problem, there's no shear force. Shear force is 0, tension is 0, and bending moment is 0 at the left endpoint, right? So I said that the difficulty of if we have these derivative relationships, why wouldn't we just integrate up from the distributed load to the shear force and then integrate that up to the bending moment? The difficulty is boundary conditions, constants of integration that you get. But this is a good one to look at for that because we have these zeros at the left end. So that just makes all the constants of integration 0, So let's see what it looks like for a simple problem like this. You'll see that in this case, it's quite a bit easier to just integrate up from the start. In a lot of problems, it's not really that much easier. Like if you have point forces in the middle, point forces at the end, you have to worry about what all your constants of integration are. But this one is pretty easy. So let's do it by integration.
Would you do something like this on an exam where it's easy to do it as integration?
No, not really. I just sort of want you to have in the back of your mind that you can do it, Okay, so what we had was this Q triangular is 333.3 repeating times X. Yeah, that's what it was. And then this was Q rectangular is 163.5. And then we had the loads over here at the end that we didn't have to calculate. Okay, well, the total Q is the sum of these two. So 333.3 X plus 163.5. And so V is going to be the integral of Q, negative integral of Q. And so that is negative 166.6 repeating X squared minus 163.5 X plus C. Okay, well, so how do we figure out that C? We know that V at 0 is equal to 0. So plug in 0 for your X's. Negative 166.6 repeating times 0 squared minus 163.5 times 0 plus C is equal to 0. And so C is equal to 0. And so your function V is just negative 166.6 repeating x squared minus 163.5x. So there's the first one. And now the bending moment is the integral of v with respect to x. And so that is negative 55.5 repeating x cubed minus 81.75 x squared plus c. I mean, it's a new c this time. I'll call it c1, I guess. And we know that this is equal to 0 when x is equal to 0. So negative 55.5 repeating times 0 to the third minus 81.75 times 0 squared plus c1 is equal to 0. So c1 is 0. And so the bending moment as a function of x is just negative 55.5 repeating x cubed minus 81.75 x squared. Any questions about that? I mean, you can see that in some cases it would be way faster to do this, right? But there is a drawback, you know. And that is that you don't have anything checking your work. So you can catch a lot of mistakes by going through Newton's laws, calculating your internal loads that way, and then using those. It's really quick to just take the derivatives of what you found and use that as a check. With this, I mean, you don't have anything to check your answers. It didn't matter much in a problem like this that was really easy to do by integration. But when you have constants of integration everywhere, things are sort of different with that. Okay, so I recommend using Newton's laws and then use those derivative relationships as a check.
We didn't explicitly say it, but we know that the tension is 0, which is why we could do this.
Okay, well, yes, we did not, right, we didn't do the tension at all. That's right. Yeah, we didn't deal with the tension at all. We don't have any,
Horizontal.
yeah, tension is pretty easy to figure out if that's the only one that you're dealing with. Because we haven't talked at all about horizontal distributed loads, which is a segue into the next thing I want to talk about. Because So tension is easy because we haven't,
Make it hard.
yeah, seen horizontal distributed loads. Well, I mean, these are all of the things we do have to represent physical stuff, right? So why would he, I mean, like, what can you imagine that would produce a horizontal distributed load? A vertical distributed load, if you had like, well, I mean, there's a lot of ways that you would have vertical distributed loads if something is applying a force over a, you know, over some distance, or you have some pile of something that's in a certain shape sitting on something. But when you see horizontal distributed loads, the most obvious place you would see it is, well, what if you wanted to calculate the internal loads in members of a structure? So, for example, you know, what if you had, I'll just make the simplest one I can think of. That's a pin joint. Let's say you apply some force to it. And let's say each of the masses of these members is 30 kilograms. Okay, and we want to calculate the internal loads in both of these two members. Well, first we'd calculate the external loads. Let me number these. And so the external loads would be something like this. You'd have a point force down here, call that RA. You'd have a point force up here, that's the force on 1/2. And you'd have this 500 Newton force. But you'd have one other thing. You'd have a distributed load like that. Okay? And you, all right, so first of all, this thing is at an angle. We're used to calculating internal loads for something horizontal. So how would you deal with that? You just turn your head. What do you have to do? 30 degrees. And then you're set as far as that goes. But getting the numbers changed into that coordinate system is, you know, something you have to think about. So, okay, for these internal loads, now you have something like that. Something like that. And a force of 500 like this. And then you have two distributed loads. And I'm going to draw it like this. You can think of it as two components of the distributed load. You have a part going this way. And a part going this way. we know how to deal with that vertical component. But how do we deal with that horizontal one? Okay, so that arises if you're trying to calculate internal loads in members of a structure where the members aren't lying perfectly horizontal. Well, okay, so first let's talk about how to get it into this form, and then we'll talk about how to deal with that, okay? So the first step is expressing your point loads and distributed loads in the desired coordinate system. And we're going to do that using rotation matrices. I'm going to do this in this class in 2D. In mechanics of materials, you'll have to do it in 3D. It's conceptually the same thing, but a little more involved thinking about the directions and stuff. But if you want to go, so okay, so if you have a vector in coordinate system 1 that's oriented, let's say like this, and you want to express the vector in coordinate system 2, that let's say it's like this, multiply the vector by the rotation matrix Q that's equal to cosine of theta, sine of theta, negative sine of theta, cosine of theta. Okay, so let's see how this works. So if we want to go from, okay, so from the example above, we want to go from a coordinate system that's oriented like this where this angle is 30 degrees to a coordinate system like this. Okay, do you see that? Let's look back at the picture. And so, I mean, you can think of it in either one of these setups, but the answer is the same. If you're thinking of it in its original orientation like this, we want to go to a coordinate system where that x-axis is along the axis of the beam. Okay, or if you're looking at it here, we obviously just want it tipped up like we're used to with the beam. Okay, so what's the angle that we need to rotate that counterclockwise to go from this to this, that's a counterclockwise rotation, right? And it's 30 degrees. So this theta is positive 30 degrees. So our rotation matrix is cosine of 30, sine of 30, negative sine of 30, cosine of 30. And so that's 0.866, 0.5, negative 0.5, 0.866. And let's do it with that 500 Newton force. Let's see how it works to re-express this 500 Newton force in the new coordinate system. So in the old coordinate system, you can see that 500 is just 500, 0, right? That's easy to visualize. So now we're going to go 0.866 times 0.5, 0.866, 0.5, negative 0.5, 0.866 times the vector 500, 0. And that's going to give us this 500 Newton vector in our new coordinate system. Okay, so how do you do that to multiply matrices? You can think of it as a series of dot products. We're going to take the dot product of this with this, and that's going to be our first element. So if you take that dot product, 500 times 0.866 is 433. 0 times 0.5 is 0, and that's our x component. And now for the y component, we're going to take the dot product of this and this. So that's negative 250 plus 0. And so we get a vector of 433, negative 250. Okay. And this is in newtons. And does that make sense with the, so we have a big positive x component and a small negative y component. Does that make sense with what we're expecting? Yeah, that's.
Did you check if you did it right by calculating a magnitude?
Yeah, sure. But you don't ever have to do this by hand. Your calculator, if you punch this in, will just do it for you, and you never have to think about how to calculate that matrix multiplication. So do this in your calculator. It's just the, you want to do the, shoot. So you want to have the rotation matrix. And then the regular multiplication symbol. And then the vector. Okay. Now it works for distributed loads too. So let's think about that distributed load for the weight. Okay, so in the old coordinate system, the mass was 30 kilograms. So the weight of each is 294.3. I didn't give lengths, but let's say these are 1 meter long. This is in newtons. So that distributed load is a constant function, 294.3 newtons per meter. Okay. So we're going to take that rotation matrix and multiply it by the vector representing that distributed load. So in the old coordinate system, how would you represent that distributed load as a vector?
0, -2.
Yep, that's perfect. Everyone see that? So this distributed load would be 0, -294.3. Okay, that's, you can think of that as like our Q vector. Okay. And if you multiply that, you get so I'm just punching this in my calculator right now. -147.15, -254.86. And this is a distributed load in newtons per meter.
Can we go over the Q vector again? I missed
Yeah. Okay, so this is straight down, so it's in the negative y direction.
It's just the weight force.
Like I'm just taking the direction of this distributed load into account
Okay.
in the old coordinate system. You know, weight just always acts straight down. So it's in the negative y direction in the old coordinate system.
Okay, so this is like analogous to finding the point force of the weight, but it doesn't matter where.
No, we're not finding a point force. We're thinking of we're breaking up this distributed load into components, but it's all straight down. So in the original coordinate system, straight down means negative y direction. So we're just representing this distributed load as 0 distributed load along the x direction and a negative 294.3 distributed load in the y direction.
Okay. So then the rotation matrix just shifts the whole.
Yeah.
direction.
And so now what we have is this. So now here's the beam. And well, we have some reaction force here that I didn't calculate. Oh, we got to go to the other class. Over here, we're going to have our shifted, this is F12. And we're adding to that the point force that we got here, 433, -250. And now we have two parts of the distributed load. We have a horizontal part that's 147.15 newtons per meter. And we have a vertical part downwards that's 254.86 newtons per meter. We know how to deal with the vertical part. It turns out dealing with the horizontal part is even easier because it doesn't produce a moment, but that's what we have to talk about next. And then we'll be able to calculate the internal loads in this beam that's, you know, in the world that's at an angle. Its orientation with gravity is different from what we're used to.
We're gonna have to rotate the reactional vectors as well.
Yeah. So we'll calculate the external loads, rotate those, rotate everything, and then we'll do an internal loads calculation. That's right. That's all. That's all we're doing. But and you don't even have to know how to multiply matrices because your calculator does it for you.